pretty much got finished chatting about meta learning. So meta learning is really just the process. Well, so part of it is learning to learn, but the learning to learn part means that, well, the agent needs to collect some information, and then from that information, figure out how to at least improve on its current policy. So it's really that process of figuring out, like, if given some really recent experience or really some context, how to use that context to, design or basically produce a policy that performs better, given either like little context, so not much experience, or not many gradient steps. These days, this also takes the form of doing different types of in-context learning. So you could give a model more examples of basically how the problem might work. And then with more and more examples, eventually the model can just figure out, okay, actually, the user is just trying to figure out how to predict a function that's just like x plus 1 or something like that. But given enough examples, it works. Okay, but there's still a lot of challenges in training some of these models. One of them is definitely having to deal with memorization. So like, because one easy way to perform well in a lot of tasks is basically just to memorize the task, and it'll figure out how to do really well on the training distribution, but it's going to perform very poorly on the test distribution because it just kind of learned, okay, no, this is task K, something from the data set, and just replicate that. So this happens a little bit more often in some of the meta learning areas. And it's part of what is overcome these days by using like larger models, larger data sets is more important because then the model can't just fixate on any particular item or detail. One way to formalize how to do this better is to basically be more Bayesian about the way that the model's learned. So in this case, it's don't make an assumption that's kind of like maximum likelihood. It just says, okay, optimize the model such that model is the best one that explains the data. Instead, be more Bayesian and say like, okay, from this data, here's a distribution over possible parameters that explain the data. And then still technically you have to sample from those. And as you get more data, the distribution over possible models that explain the data will reduce over time. So one way to often overcome this a little bit is you can learn some type of, some good adversarial policy. So this is, you can also have another mechanism that's basically trying to make it more tricky for the meta learning process to just find corner cases. So it can present kind of like random tasks to it such that now it can't just overfit a particular set of tasks. That's to learn to be able to adjust to any new ones. Okay. All right. So that kind of covers a lot of the meta learning aspect. Now we're going to be talking about a couple of different models where now the specific problem is figuring out how to generalize, but generalize to, I'll call it robots of different design. Sometimes it's called different morphologies or different designs. There's a couple or different embodiments. They're all the same term. So it's basically this problem on the right is what, in this case, if we wanted to design a policy such that it can control any of these robots, like one single network. Most of the stuff that we've talked about in the class so far has always been like of this form. Like here's a network, it produces some action, and these are really both vectors, state, it gets inputted to this model. But F here always has a very fixed value. Like there's always a fixed number of features. There's always just, like S0 down to SK. And then there's also like this vector for actions is going to be S0. Let's say this goes to AJ. But these are always fixed. Like the whole data set is just that stuff for the states that ends up being inputted. Nothing changes about the size of this vector. But now in this new version of the problem that we've got here on the right, okay, if you can see, you look maybe a little carefully. I mean, for sure, this robot here has a different number of joints than this Franca arm on the left. So how can it be possible to make a policy such that it can actually actuate both of these? The state input is a different size vector. The action output is also a different size vector. Is there really any hope in being able to train some model that'll learn some structure if all the vectors keep changing? It's actually a kind of tricky problem, but the goal here is to figure out, all right, is there something still common about the dynamics that exists, even if some of the morphology changes. So there is at least a really high level version of this where like, okay, all of these robots, they do operate in what is essentially this Newtonian mechanics. So there should at least be that concept that they can generalize over. Here, being able to capture data. And if the information that the model is being trained over is organized carefully enough, maybe it can pick up on that and then be able to generalize to, robot question mark here, which I'll say could be anything, but, being able to extrapolate to any model is at least not easy. Okay, does that make sense so far? It's a weird version of a problem, but we've already talked about some models in the class that can be used on this type of problem. But I just at least want to poke a little bit clearly that, okay, some of the papers, like the OpenX embodiment dataset that we've talked about, a lot of the transformer papers, they don't technically do this. Even if some of them, like even if the dataset is called OpenX embodiment, the state space and the action space don't change. The output for the model is always end effector position. And that's not going to be helpful. At least, for example, the robot on the bottom right has 2 arms. So now the model at least needs to output 2 end effectors, minimum. But in most cases, this is a very specific version of this problem. And now, so like this talk is very much treat this totally more generally, where almost like any robot morphology can be actuated and they'll be controlled according to joint torques and like pose state inputs at least. And let's talk about just how the heck can we possibly get this to work? Okay, does that make more sense? Now, at least the prior work we've talked about, even though it's calling itself like more OpenX embodiment, it's not at least explicitly doing that embodiment generalization. It's doing it implicitly, which can help, but it's still not as nice as you might want it to be. Okay, so let's start with a version of this that's kind of like the I don't know, the slower pitch version of this for now, where, all right, we've got a bunch of different robots. And in this case, they're all quadruped robots. Maybe you can all see them. I'll zoom in a little bit. Not that that helps because that made them at least a bit more pixelated. But the part here that isn't as much of a challenge, even though I'm kind of likening it into the last framework, is also being able to figure out how to control any of these robots. So the joints and action spaces they're vaguely similar. So at least like the length of the feature vector is the same. But like this is one of the simulated robots, but like the A1 robot that's here on the left, it seems to be even more pixelated up on the projector screen than it is on my tablet. So that's a small robot. It's about this big. Actually, I'll get to see one after we're done this portion of the lecture today. It's only about 10 or 12 pounds. But then there's also things like the Alien Go is different. That one's about 40 pounds. So the torque that it can actually generate at the joint is significantly larger than this other robot. So the effects of applying the same amount of torque on these 2 different joints are not the same for these 2 different robots. And then Spot is another version of this. It's also going to be, I think it's a bit heavier than the Alien Go. Don't test me on these questions. I have not weighed these robots personally. But at least you understand the action vectors and state vectors will be similar for this first paper we'll cover. But it's really the effects of applying like those torques on these different robots will have different results. Okay, makes sense so far. So then here, what can be used to at least solve this version of the problem is using a version of sim to real. We've basically already talked about like this problem, being able to train a conditional model over a sequence of recent observations. And then it can use those recent observations to figure out basically which robot is it currently controlling. Because the observations will help it be able to learn to detect like the mass of the robot. Because if it applies, a sequence of torques on one of the legs, how far does the robot actually move according to that information? So it can start to determine which robot is actually being controlled. And then this latent model, basically it can be used across morphologies. And the things that are still different are like the masses of the joints will be different. Frictions will be different at all the joints and even the ground, as well as communication and sensor delays, which are usually one of the harder things to deal with whenever you're trying to manage some actual hardware. A bunch of other options, etc. Okay. And that's where, and then this is basically the model design that's used for this paper. This is use what is essentially an MLP, so nothing too fancy for the actual neural network. The part that ends up being at least a little novel, or you can recall it from the sim to real lecture, is actually part of the input is not just a state. It's going to be like the recent 15 time steps, like maybe half a second of information about how the robot has been moving. From that, and then there's this. Sometimes this is a nice little method to say, okay, basically, if the model starts out with nothing, it still stands. So now how many of you are like familiar with good network initializations, or at least understand the idea that like deep learning only works because of the random parameters of the network are initialized kind of carefully, right? Makes some sense. Basically, this is kind of doing the same thing, but for a robot. The initial parameters, hopefully for the network, should have like zero mean. So it'll just hopefully output zero when it's given a random state. But then zero mean for a robot would mean it'd probably fall on the ground. So then what can happen here is a nominal standing position is also being inputted. So it's now zero mean, just has the robot stand perfectly still, which is a much better like initial configuration than like no torques and just collapses on the ground. So in many ways, you can think of this as like a version of trying to provide like a good network initialization to the policy. So it starts out in its RL exploration area in a much better situation than knowing nothing and kind of like falling on the ground like a, I don't know, pile of noodles or something like that. So that's just a little bit of an aside. And then here, control, simulate each of those robots, train one policy across every single one of those simulated robots. So just like in our for loop for being able to collect the information, where before it was task, now it's basically generate a robot in one of these simulators, roll out that robot in that particular simulator. I think all the same task for this paper, and then collect, a number of trajectories for each of these robots, then perform one gradient step using this model. Does that make sense for the RL algorithm? Okay, good. And then seems to work pretty well. Okay, so these are a bit small, but the idea here, okay, the gen loco, which is the method used in this paper across morphologies, is the green line. So it basically tends to, it's kind of ends up in a bunch of nice properties. So I know that the reason I started with motivating this particular problem is generalization, right, to some new policy. But there are so many other benefits that come from this. So one, okay, sure. Generalization. Another one is robustness. So that means if there's a little bit of sensor error in the robot that you have, the model still gives a really good prediction. So in this case, it's because this model is now being trained to like learn to deal with this process. If like you get a slightly different robot, well, a version of a slightly different robot is one with a little bit like one of its sensors corrupted. So then here in the results for this paper, it's sort of okay. If the size of the robot is just kind of changed randomly according to this parameter, it still gets good performance. It tends to be like work well for a while until the size factor gets about 2. And then you can also change like the length of some of the joints, and it's still able to figure out how to walk pretty well compared to a model that's just trained on one robot. So you get this robustness, kind of for free, mostly because it's really aligned with the generalization properties that we care about here. And then there's a different version of this, varying other morphologies, and a bunch of other like size factors here as well, and doing some spinning, things like that. And then the orange line is just the exact same model. So like nothing about the RL algorithm changes. It's just only trained on the A1 robot. So the single kind of small black quadruped. So this Data diversity helps force the model to learn like a better function over robustness and generalization. Ends up being easier to apply stuff to the real world. Uh, oh darn, they had some real world experiments too. So then you can just apply this to any quadruped robot. Maybe a bit easier thing to like sell and produce than say like, here's a policy. It only works on quadruped robots inside of Glenn's lab. Not very useful for everyone else. So this ends up being a much more reusable policy. Okay. Any questions so far about this model? Okay. All right. Well, then let's get a bit more involved. So generalization and robustness are a benefit of having this model on the right. What are some other benefits of being able to have a model that works across robots? Yeah. Sorry? Mm-hmm. Yes. So that's going to be, I'll call that fine tuning for now. This is better than like random init, we hope. Although I'll be a bit honest right now, at least for the robotics community, we're not making a lot of progress on that. Like it seems to be hard. Maybe I've seen a few successes, although they're unofficial and not really published, on at least taking something like Pi Zero fast and fine tuning it. But for most of the robotics models, the amount of data that's needed to fine tune isn't basically the model isn't providing a lot of improvement. So there still needs to be a lot of research done, to be honest, on figuring out how to construct the network well enough to make the fine tuning process work. Or maybe there's a lack of data at the moment. Could be either, but that's a good goal. Okay. Other one? Any other ideas? Uh, mhm, indeed. Yeah. So, well, it's because this model might be available. Maybe you can use it to help design hardware. Has anyone ever tried to make a robot from scratch before? Design anything from scratch before? Okay. How many of you have tried to iterate on network design for like your learning algorithms? That's probably a handful of people. All right. How easy was that? How many things did you iterate on before you kind of felt maybe this one works better on average than the other models? It's not an easy design problem, is it? And that's just like network design. So this is okay. Now what if you wanted to evaluate whether or not one robot is better than another? You need to manufacture the entire robot, but you'd also need to train a policy for that robot as well, which also takes time. So if you could handle this model and have it do co-design, it means that hopefully like when given a setup for the actual model, or like here's a description for a robot, it can at least output a policy. And from that, hopefully like a Q function, and there's a couple of nice papers on that that'll like predict, at least given some prior training over morphologies and using the Q function, is like maybe this is an okay design as a way to select stuff. A colleague of mine, Kevin Luck, does a handful of that work if you're interested in that area. Very awesome area. Okay, other ideas? Hopefully people are already starting to understand the stories. Like if you make this, like the benefits list is really long. There's still one more, at least, that uh, gets me really excited about this design. Maybe I'll ask this question. How much robotics data is there? Not a lot, right? And all the robotics data is usually data per robot. So that means like even the OpenX embodiment data stuff only works for like things with hands and end effectors and images. But there are self-driving cars, there are drones, there are, to be honest, there's submarines, there's aqua things, there's boats, there's other types of cars, there's humanoid robots. There is data for all of these things, smaller amounts, but instead if there's a model that can train over all of the data from all of these things, now it's no longer, oh, I've only got data on my individual robot, which is like basically no data. Instead, having this model that can chew through a whole bunch of data from any type of robot means more data. It can just now make use of data from all of these other morphologies for robots. And this, you can really go pretty far on this kind of claim too, which maybe like anything else that's collected data for can also be used. So these are all a lot of like prime benefits, like why pursuing at least this particular model class ends up being a huge advantage. Okay, makes sense. We all really want this thing now. Now we even understand it a bit more in our bones about like, fantastic, this would be great. If only we can make it. So now let's get into some more details about how to make one of these. So one of these is that I'm going to get into. So now this is just going to be particular about designing different versions of robots. And now we're going to treat this as a graph problem. Because basically a robot, at least in like a rigid body simulation, is a graph. So it's got some links, it's got some joints, it's got some elbows, things like that, and motors. And this is where I'm going to talk about, okay, there's at least one data set for this. We're like, okay, this is now basically our training set on the right, where we can partition off, train our model, like over this distribution ends up being the training set. And then this distribution here is our test. And the thing that we can at least take advantage of here is, well, now the training set is described by graphs. Like these are all linked together. It's pretty easy actually, like the Mojoko simulator, to just ask it to generate the graph for how things are wired together. But then how do we make use of this graph in order to understand all those different morphologies and generalize over them? So this is, at least in this prior work, I'm going to talk about shared modular policies that's basically started doing this using graph neural networks. And then there was kind of a transition more in the community to get into using transformers more. Short story is because, as always, researchers are lazy. And by that, I mean, just want to have less and less assumptions needed to use the algorithm. So let's start with the graph problem. This is basically part of the evaluation was standardized. So partly here is like, okay, well now my training set is a robot. It's not just like change the reward function to be velocity 1, 0, instead it'll be velocity 1.1. That's not really much of a task change. Now this is the whole dynamics change for the actual model. So it builds off Mojoko. There's about 45 different agents. There's a couple of different papers. There's even one that kind of procedurally generates morphologies, but they don't look very natural. So maybe take that with a grain of salt. Procedurally generating stuff that looks maybe quite bad may not actually be helpful in terms of like the training distribution or morphologies to train over. Still good to have some good diverse morphologies. So the idea in the first version of this, so like to try and generalize across all these morphologies, was to develop a network that would process over these shared modular policies. So this was basically training a model, just the one policy to control them all paper, such that there was really like the overall morphology for the character would be processed twice, like once from the top down, if you were to like line up all the joints into a sequence, and then once from bottom up. And then the outputs from those two things hopefully end up matching. It's an interesting way to kind of like start to construct the graph for this. But I'm going to get into a different version of this that's at least a little bit more detailed, because what they're using here is a graph neural network. Are people familiar with graph neural networks? Got one or two? They are an interesting version of a network, and I'll like explain them here. So the idea is your network is literally a collection of nodes. So there's no longer like single feed forward network. And the hope is to be able to train this collection of different nodes in a network such that you can get good outputs, in this case, to control a robot. So this might seem weird. Like, how do you take this model and then feed it into a deep network and output an action? Because Glenn said, like, someone's going to come along and like remove D from this, But our deep network model only takes in fixed length vectors. So like nothing works. But it's actually not how this is going to work. There's a different way to kind of train a neural network to basically get around part of these challenges. The idea is okay, there is technically like a full feed forward network that exists if you're careful about the way you construct it at each node. So if you want to be able to figure out what the output at A should be for like controlling an individual joint, and we're using RL, or we can just say we're doing supervised learning. So we've got a target that should be outputted for that joint. And then we've got inputs that go into all these other values. So this would be like a NLP and a different NLP. But basically, once all these inputs are set in the network and they're processed through the different nodes, the output should be like the target value for A. So it's kind of this interesting way of being able to construct the network for now, like maybe for every batch, a particular target node is selected, a computational graph is generated for that node. So then you do this for a whole bunch of different nodes, and they're all generated, and then you have to do like the feed forward pass to those computational graphs in order to be able to generate the output, and then compute the model loss so that the model does predict the proper output for those individual outputs. It's an interesting model. It gets a bit complex when the graph gets really big, because then this gets much, much deeper over time. But it is at least possible to train these. Okay, does that make sense so far? Any questions about graph neural networks? These end up being really great, especially for things that we know have this graph-based structure. So for example, like AlphaFold is built entirely on graph network design because molecules have a really strong graph structure. So you should basically use something like this. It's got that prior built in already. Okay. And then, okay, so we basically use this template. Here, I'm just showing the process how like the computational graph can be generated for different nodes. And then now, all right, our robot policy is basically the same problem. There's a bunch of nodes for like action 0, and this will be index like 1 of the action and action index 2, etc. for each of these chunks of the policy. Then basically encode all of these into a graph neural network. And then when you need to get the output for an individual chunk in this particular joint, then you can kind of, I don't know if you've done this dangling tree thing before, but kind of like pick up that node and then you can see the computational graph kind of like dangle below it as if you've got a tree, and then you can then propagate the loss through that network in order to get like the probability of the action here to match more towards the action, the feature in the action dimension that would correspond to getting higher reward. So this is how to literally just take the morphology graph that's embedded inside a Mojoko, turn that into a graph neural network, and then use the targets as the actions for the output. Okay, makes sense so far? Okay, so, and this can work pretty well. It does some good transfer. It's easy to build a new agent because then you can just have various sizes. So the part where this works over various variable sized graphs is that training process on the last stage. Like it learns to be invariant to the graph design in terms of the way it computes this computational graph. So it'll generalize to different kinds of graphs. Okay. So you can go look at some of the results for the shared modular policies paper. Okay. But like I said, all right, so as researchers, we want the fewest assumptions or to be, like as lazy as possible. So here, one of the things that was necessary to construct that graph is it was required to be able to know like the wiring for the graph, the actual morphology, like the millimeter distance between all the joints, how they align, where they go. But is it really realistic to know that graph? All right, how many in the room right now could tell me how long your right forearm is right now? None, right? Okay, and you've at least probably used your right forearm more than you've used, I'll say, for example, like any of the robots in my lab that we'll see later. So it's not really realistic to just say, okay, we'll just always have access to this graph. I'm giving kind of a harsh example for talking about people, which you're kind of used to in yourself, but like even robots kind of break down. Like the length between joints will change over time. The fingers get messed up. The joints become like more rigid over time. When the motors start to heat up, the friction in the elbows change. So relying on this information for it to be given is not going to scale well. It's not going to make really robust systems over time either. So let's at least see, all right, how much of this information can be learned from context or for some of the data rather than like assumed knowledge. So this requires a lot of prior knowledge. And we still want to tackle this problem of like training over a bunch of morphologies and eventually testing on one held out one. So then how can we construct this without needing at least the connective knowledge for the graph so far? And it's really because at some point, hopefully at least the robotics stuff that we'll produce that others will use won't require a person to take this class, at least before having to use a robot for something that's already been done. That would be a goal. Okay, does that make sense? We all want to be able to use robots easily. Don't want to have to learn the morphology. Certainly don't want to have to learn how to use ROS, which is even more tricky. Okay, great. So some might say though, okay, but if you leave out that graph information, isn't the policy going to perform worse? Because now it doesn't have this like prior information about how the robot is aligned, how much it might weigh, how all the joints are. Surprisingly, in a lot of research papers, no, including that extra information actually results in worse generalization performance to new morphologies. Potential hypothesis is here, well, because of the network needing to rely on that information, and because it's really hard to get accurate, and there's not a lot of morphologies, it's not really going to learn well how to generalize to new morphologies if it also needs to base its decision on like a perfectly accurate measuring system for the morphology of the robot. So it's probably going to be biased and kind of pick up on mundane differences between these connections. Okay, so then here's some examples. This is where it's kind of this version and a star and a line. You can see the version that does sort of a different connection that doesn't really rely on morphology information can actually start to perform a little bit better than the one that doesn't include the morphology. And in this case, the connectivity information. So, okay, so this becomes, all right, can we train a policy without morphology information? So for one, well, now if there's no morphology information, it's really hard to figure out what the graph should be because somehow it will need to be learned, like the actual connectivity in the graph, which is not going to be easy. But, what are we all pretty familiar with by now that does an okay job of figuring out how things should be connected together? All right. The answer to that is basically transformers. It's their attention mechanism is basically doing something that's, well, it's kind of a more general form of figuring out, all right, how should everything be connected together? It's doing it in an information way instead of like a morphology way, but the same concept can be used. So here, replace a graph neural network with a bunch of self-attention layers where there's a node now for like each joint. So there's one for a torso, other limbs, etc. The transformer will figure out, all right, given this current number of links, figure out how to attend over every other link that's in the system. And then from that, produce an action for each of those individual links. So it might only need to attend over like a few of them. If it's the elbow, maybe it only needs to attend over like the wrist and the upper arm. And it can kind of ignore the information from the rest of the system. Okay. Does that make sense? Everyone like has the design for transformers like so ingrained in your head that this is obvious? Okay, good. Good thing to do anyway, because it seems like everyone is asking transformer questions on interviews lately. Just won't go away. So then in this, here you can basically use this process, and now no explicit connectivity information needs to be provided. The model will learn it while it's training. What is at least helpful in terms of connectivity information to figure out what is the best action to produce. So it doesn't need to learn to connect everything. All right. And then this is a little bit about the results. So now this is SMP was the one that used a GNN, and Morpheus here is now using separately some of this information, but not as much connectivity. So despite this lack of structural information, like a Morpheus that uses a transformer tends to generalize much better. A bit about this. The fun part is, so node features alone are enough to learn a policy. It's good. Okay, so before, basically there was a list of all of the joints and then also all the connectivity between the edges, and now it's just the list of the joint information. Well, it seems like there's really enough information just in the links, the data for each link for it to figure out like what is the use for this link in the overall model. Because, like everyone in here, your right hand is always on your right side. And like the access that you can control it is also always on the right side. So because of that, just giving the data for like its rotation and basically its position is enough for the model to determine this is probably a right hand or a right wrist, at least one of the two. Just from the node information about like its access right now relative to other things in the actual robot. So it doesn't really need that extra morphology, like connectivity information. Okay, does that make more sense here? It can identify links without needing the explicit graph and then figure out how to generalize over them. Okay, but is there still a slightly better way to provide some of this morphology? Because now this also needs to have, at least in the Morpheus case, there was more details about what was in the actual node descriptions. So there was some extra information there. So this is where, okay, is it possible to replace the hand design graph? Because this particular model is still trying to like learn the graph. So it still there is a strong assumption that the graph exists. It's trying to learn that from the node information. But is it possible to basically learn just a sequence of discrete tokens for a morphology? So now this is really not even node information. Like it doesn't say as much about what it is, just that it is a joint and it's got a vector of 6 numbers. So this can work because of the use. You kind of think of this as just a type of sequence to sequence problem. If you read in basically the joint information for one robot, it should then be able to output the actions for that robot. The same thing that's used in like the vast majority of language models that are used now. So it's kind of like, can we just train ChatGPT or some LLM model that just, okay, it's seen a bunch of these inputs for this description of the robot's vector that describes this particular pose, and then it'll output the action control for like the torques at that time. And just ignore most of the other structural details. So this is taking advantage of these sequence to sequence models and then building on this. And this is basically the overall thought process for this problem is instead of necessarily trying to provide explicit information on what the robot is and how it's designed, kind of do this sequence to sequence problem, and then like something about the description in the sequence will basically help it infer the morphology. So before it would be train some model to take in, tokenize a bunch of these items. Maybe it's done in words. There's maybe a better tokenizer. But the trick is, if we're going to use transformers, we kind of need to find a clever version of a tokenizer. Okay, so what are some ideas here? If you're given just a pose for a robot, how would you go about tokenizing that pose in order to give it to a transformer? Any thoughts? I didn't purposely leave this out of homework too, just to trick you all right now and come up with this new problem, but it comes to mind at the moment. Because the robot's not made up of words. You certainly can't use like ChatGPT's tokenizer on continuous values. Any thoughts? Has anyone ever seen like a good LLM that tokenizes even continuous values before? No, not easy. In fact, like most tokenizers for LLMs are designed strictly for characters. They're quite terrible at floating point numbers, even to begin with. Okay, so there's one, I'll say it's really non-obvious, but there's kind of one clever trick that if at least the answer comes mostly from some knowledge of how computer graphics works. So in computer graphics, What's normally the information that is stored for like every joint in animating a character is just its position and rotation. And that is enough to feed into an animation system to then animate something. Is that going to be enough information to basically now learn a policy that can generalize over different shapes and morphologies? Well, it turns out that can actually work pretty well. So for here, for all the robots, basically tokenize them all into individual joints. And then each of these joints, just for a little bit more detail, they're always going to be vectors of 6. This will be like the position at X, position at Y, and also the rotation X, rotation Y, and Z. So now basically what was the whole observation vector, that would be, like hip, knee, etc. Each one of these is this 6th element vector. So basically every joint in a robot is always defined by 6 numbers and the way that it moves. So you can tokenize the observation into these chunks and then basically train over a bunch of morphologies, let the robot figure out, or sorry, like the transformer figure out, okay, what tokens does it need to attend over for just these groups of 6 numbers in order for this to learn? Does that make sense for the design now? We also tried long story short, we tried not using 6 numbers. We tried other versions of this. Technically, it should be possible to like use the transformer and then just use like every individual value and tokenize by floating point number. We could never get that to work. We spent like 4 months trying to get that to work. So there wasn't quite enough grouping properly, because then the transformer would still have to learn that those 6 numbers always correspond to the same joint. So at least if we provided that bit of prior information for like, here's the 6 numbers that describe the joint's position and rotation, and it doesn't have to figure out how to attend over that. It was much easier for it to figure out like what was going on and what it could attend to. And figuring out this. This is often also called the routing problem, which is given kind of a graph and a whole bunch of nodes, like what's a good way to connect all these together to get the best performance? It's figuring out, given a pile of nodes, how do you connect all these? This is if you're one of those people who really likes old school, awesome computer science graph theory stuff, go check out the routing problem. So it's kind of what the transformer is trying to figure out now is, given this data that describes a morphology, connect all these together to solve a version of the routing problem to get the proper output. Okay. So then the anymorph architecture basically build on the sequence of token design. Here, there's a bunch of joints, tokenize these such that they all get embedded from a state. This is going to be the position, angle, and velocity. Tokenize the individual joints. So here is going to be like some labels for like limb. They're not really labels. There's going to be like index IDs for like whether or not it's a hip or something like that. And then those will correspond to this information such that it can just figure out how to infer the morphology from that information. So no individual graph information. There is a little bit of an indexing here for if it's like a wrist or something like that, and it's a left wrist, they both get the same ID. It just says like, this is the wrist-like thing. And to be honest, there isn't that much variation over robots such that you'd need to have a really large collection of token IDs for different type of body parts. Maybe robot designers are just not very creative and they're still really fixated on the way people are designed. Really seems that way by the amount of humanoid robotics companies that are being made. And then from this, just train a transformer. So the input from the state gets fed into the encoder, transfer some of that stuff to the decoder, decode the number of actions. And in this case, those groups of 6, which are these blocks, however many blocks there are for every joint, always determines the number of features in the action token. So this is always if n is the number of joints, this one is always n times 6. This one is always n. Just because of the way the math happens to work out in this particular design. Okay, pretty clear now? Everyone could go and implement this again with your eyes shut. You don't have to worry about it. Maybe you have to use cursor at the same time, but you'll probably get there. Okay. So then again, so this also works really well. It ends up being even more robust than some of the prior methods. Neat thing about this too, for this version for any morph. You also get better sample efficiency. Now that it's like basically more efficient to be able to train this model across multiple morphologies than it is to train all those morphologies individually. So we're starting to get towards the sample efficiency because of this generalization and network structure. It was a bit tricky to get there, a little bit more structure than maybe hoped needed to be provided, but it certainly helps increase learning speed. It also helps increase robustness. So here, this is if a couple of the robots are left out for that test set. Here is zero shot transfer, no fine tuning, still maintains, like in this case, if it's getting 2000 performance, okay, it goes down to about 1100, but that's still pretty good in terms of rewards overall. So the robustness kind of comes as an advantage. So that's for zero shot transfer. There's also another way to look at robustness. So if you design an experiment such that random noise was added to joints on the robot, this method that was using the transformer for the generalization and model would end up kind of scaling pretty nicely towards the amount of random noise that is added to each joint. So this is a kind of weird experiment, but basically if zero is no joints have any random noise added to them, and then 0.5 is half of the joints have random noise added to them, and this is like full random noise. It degrades pretty gracefully in terms of the amount of noise added to the actual sensor systems. So if one of the joints happens to like, I don't know, the robot accidentally like bumps into a wall and knocks one of the sensors, it can still perform pretty well as just like one of the givens from the way the model was designed to be robust to changes in morphology. And somehow this happens, but if we at least take a look at the attention mechanism, where basically this is all the sensors, and I think this is an entire trajectory on like what is activated in the activations, it's actually extremely sparse. So the model is only paying attention to very few joints, like for an individual node in the way the model is learned. Okay. Questions? Make sense? Again, big generalist models, or at least like morphology generalist models, come with a lot of benefits as long as we can get them to work well. Okay, so from any morph, I think we can really use word-like representations to tokenize robotics, improves a lot of zero-shot generalization. There's definitely still some challenges. So right now for this model, there wasn't an obvious way to combine it with images. Although these days there's been more work on multimodal models to be able to train them well. Short story is it also takes a long time to train these models. And then when you add in images, it takes even longer. So training these models takes 3 to 4 days because the transformer is slow. The simulation is fast, but now we're waiting on the model to actually just produce actions. So adding in images will make that even slower. And see how this can scale to more tasks. At least in this work, the task was one thing: run to the right as fast as possible, which is our favorite task in Majoko. So adding more task variation will probably be needing to change the model design there as well in order to help infer what the task is. If you want some info on that, see all of the slides before this on meta learning for how to infer the task and combine those methods together. There is some nice piece of work. So if you want to extend a bit more on this, you go check out the Metamorph paper, which is kind of done in tandem. Similar ideas, but also will include some video. And here it's just kind of like tokenize that video normally and also feed it into the transformer. Works pretty well for generalization. And then here is a different paper where now it's a really harsh one. Maybe some of you have seen those videos from Boston Dynamics where they like kick the robots and hit them with sticks. So this is kind of that example where like mid trajectory, it needs to adapt to an online change where some other agent comes along and maybe like knocks one of the joints really hard or removes one of the screws, and it has to still adapt. So like mid trajectory adaptation, not just zero shot generalization. Okay. If you want to know more, find me after class. All right, so that was those slides for a lot of details on kind of the outlook here. I suppose it works really well to be able to design one of these generalist agents. There's a lot of benefits. There's still going to be a lot of work to be done. There's not a lot of data for robots, so it's hard to train a lot of these policies and evaluate them. That's still going to be a challenge. So most of the work is still done in simulation. And it takes a long time to train these models. So people aren't really using like VLA models for this problem as much right now, just because it takes like half a second to make a forward pass in a VLA. So good luck trying to iterate on different types of network designs and then seeing which ones perform better. Okay, and then we'll get back to the last bit of the slides here for a minute. So there was Anymorph, and then there was built onto this is a newer version that was published at the most recent version of Coral that, okay, tries to relax this problem even more. So in Anymorph, some of the information that was required were those IDs that kind of identified left or sort of like wrist versus not wrist versus shin, hip, etc. And if you probably didn't notice, but for Anymorph, all of the robots in the simulation were just capsule-based weird things that only worked in 2D. So now this work basically takes this problem of morphology generalization, applies it to real hardware, and also changes the transformer a little bit so that it's not required to include like that node ID information that says like wrist versus elbow. So in this, there's a slightly different attention mechanism. So there's still joint observations. So this is the same thing that was used in Anymorph, which is just like the six feature vector. But here some joint description information is going to be used as well. And this is more general to compute and doesn't come from the user. But this is going to be stuff for the observation of these positions. Joint description is just going to be like relative distance to the root. Is it like the end of the actual chain for the actual robot? What's rotation axis? So this is all stuff you can compute for each joint, and it doesn't have to be manually said, okay, this is a hand or this is an elbow. From here, the idea is where basically this joint description information is trying to act in place and become that version of providing that node index. But here it will be learned properly, like from scratch, without having to manually provide that node matching information. So now at least the user doesn't need to go in and look through the URDF file for the robot, add in node IDs for what they'll be, like basically wrists for both of the robots or something like that. It'll just learn those particular like descriptions. And then from that, it's fed into this upper chunk here that basically acts as part of like kind of like the position information that's given to like a transformer to figure out, okay, now given this description information, where should this thing actually like exist and pay attention to in the sequence? And maybe a slight adjustment here where the foot information is kept a little bit separate, which is also included. It's probably just like part of an artifact. Maybe that can be improved and included in the overall model in the future. Okay. But again, so this model is like a bit of a specialization. Well, it's a slight generalization of Anymorph, but it also gets really good performance. So this is the URMA model, where now this gets better performance pretty good performance when it's trained over all robots compared to just like a multi-head baseline, but it does generalize better. So here in this case, this is zero shot with foot observation dropout, so it can pay attention to the feet more. So here this model particular version of a transformer still generalizes really well to that robot design that was left out of the data set during training. Okay, does that make sense? Still good? All right, and then we've got our last version of this, which is, okay, there's this paper called Scaling Cross Embodiment, which is the idea like, okay, can it be even more flexible across embodiments? And now this kind of goes more back to something like the Octo model, where it's got a transformer. It's more like a vision-based model. But how can that model be adjusted such that it can handle different action dimensionality in the output? So in this case, so just pretend we've got octo so far because the model's pretty similar to that, and still expand upon these morphologies, and it can take vision as input. What is done in this case is a little different. We're now basically the model ends up training a bunch of different heads. So before there is a shared like transformer embodiment backbone, but for every kind of variation in morphology, add a head that's going to be an output onto the network for all of those different types of morphologies. So it's not necessarily doing more of the like kind of structured attending that was done in some of the prior works. Here, this is instead, all right, let's add a couple of particular types of heads whenever that like action feature dimension changes. And then you can just train all these and kind of hope a little bit that there won't be too much variation over the differences in the action heads. Okay, does that make sense? So there's an action head for manipulators, two arm manipulators, another one for kind of like position-based locomotion or navigation, one arm manipulators, and another one now for quadrupeds. And then you can just keep adding heads onto this in terms of if you've got a new robot, add a new head, train it a little bit on that data. Okay. And then this also tends to actually work pretty well. So now this is the other case of for all of these environments, the idea is to get one policy that can control all of these robots, where before, like Octo doesn't have data, so it couldn't do this version because it only has data for single end effector control arms. It also couldn't do this version either because there's no arms on those robots on the left. It also couldn't do that version either because there's no arms. So it can really only process data for this at action heads. Yes. Mhm. So, okay, that one I'll have to triple check. But from what I remember, like actually in the paper for the design, they actually don't worry about proprioceptive information. They kind of like hope that a lot of the information will be learned from the image. So using some historical stack of the images, then like, is it possible? Certainly for the arms on the right, you can learn the proprioceptive information that would describe the state for the arms on the right. Sometimes some of the navigation as well. It's a good question. I think I'll have to double check how that was done for the quadrupeds. And even for the most part, Octo didn't use proprioceptive information much either. It's mostly all visual information. But remind me about that one in Discord. I forget the detail exactly on that one. But to be honest though, that seems to be like for the group and aim for people that are doing vision-based robotics, the hope is the proprioceptive is basically just in the image somewhere. So you don't necessarily have to figure out how to do like the careful attending over and tokenization of the proprioceptive information. That might work well in the future. It just doesn't seem to generalize quite as well because there's less structure that can be implied there. Okay. And then, yeah, so these are all a collection of some of the different embodiments. And then this is some of the performance for using some single robot data sets and modeled how they're trained. And then here, using this version of Crossformer gets a little bit better performance on average across the different morphologies or embodiments that it's evaluated over. Okay. Other questions? No, no last questions? Okay. So that's basically it for the cross embodiment stuff for today. That's most of the recent work. This is still going to be like a large area of research for a couple of years at least, because it's not easy to do this cross embodiment and there's not a lot of data. But yeah, so then let's do two things now. So we're going to take a break. And by that, I mean, if you're coming along, pack up your stuff. We're going to go visit the lab in the other building where I'm going to show you, well, Kirsty and I are going to show you how to collect some data using the Droid data set. So maybe you can even use that for your own project. We're also going to show you how to use the Widow X arm, which is what you can use for your own projects as well, and how that software works. Okay, so yeah, back up, go for a short walk. All right.